Hello, Professor Sargent here with you again. I've been asked by another creator to show some additional options for solving a problem that he had posted a solution to. His video is titled Math Olympiad Preparation, Solving Exponential Equations. And there were some interesting comments being made. Here's the question, first of all. We are asked to solve 2 to the a plus 8 to the a equals 68. As is often the case, some of the comments regard saying, oh, this takes a long way to get there. I can just see the answer is such and such. Well, what if what you have found is one solution, but there are multiple solutions? So some of this is going to be repeating what Super Academy, the other creator, had already done, but in some cases I will handle it a little differently and try to go a little bit beyond. All right, so the commenter said that finding that a equals 2 is a solution is very straightforward. Okay, let's rewrite 8 as 2 cubed. Also, 68. 2 goes into that 34 times. And then 2 goes into 34 17 times. Furthermore, you can rewrite 17 not as a power of 2, but it is 1 more than 2 to the 4th. On the left-hand side, we'll use the fact that when you raise something to a power, and then that is raised to a power, you multiply the exponents. On the left-hand side, I'm going to factor out 2 to the a. So factoring is closely related to division. I'm left with 1 from the first term. And I'll subtract the exponents, 3a minus a, to leave me with 2 to the 2a over here for my second term. And further, I'm going to rewrite 2 to the 4th as 2 squared squared. So, the two places where we see a here, we have a matching up with the 2 here, and then let's write this as that 2 to the 2a, I could write as 2 squared to the a. And so I have a here and here, matching up with the a here and here, giving us a equals 2. Okay, but there's more to it. Now, the next thing that Super Academy did was to commute the multiplication there, and then using that same rule of exponents I mentioned a moment ago, you said let x equal 2 to the a. And so what we have is x plus x cubed equals 68. Here I'm going to differ with how I show that a equals 2 is one of the solutions. When a equals 2, x equals 2 squared, or 4. So what would be a different way of showing that 4 is the solution of this? Without just plugging in and also gaining additional information. Let's find that out. So I'm not satisfied with leaving it at a equals 2 as a solution to the exponential equation, or similarly, the x equals 4 is a solution to this polynomial equation. I'm going to put this in descending order and subtract the 68. Since we know that x equals 4 is a solution, x minus 4 is a factor, and we can do long division to find out that we get a polynomial without any remainder. Quicker approach is something known as synthetic division. I have for the x cubed a coefficient of 1. I have no x squared, so a coefficient of 0. For x to the first, coefficient of 1, and the constant term, negative 68. I bring down the 1, and then I go through a succession of multiplication and addition, multiplication and addition, multiplication and addition, or as I call it for short, MAMA. Take what's in the bottom row times the solution that we have found. 1 times 4 is 4. Go up here diagonally to write it underneath in the next column. Add. Take again what's in the bottom row, multiply by the 4. Now we've got 16. Go up diagonally to the next column, write it underneath the 1, and add. And then the 17 times the 4 gives us 68. And when we add that up, we get 0. That's telling us no remainder. Furthermore, that is telling us we have factored x minus 4 times, well, what do we have to multiply x by to get x cubed? We'd have to multiply x squared. So that 1 there is a coefficient for x squared. Our other factor is x squared plus 4x plus 17. We already know from the first factor that x equals 4 is a solution. As for the other factor, the other creator, Super Academy, I seem to recall that he applied the quadratic formula. Well, that'll work, but I could complete the square. Looking at since that's a 1x squared, I'm ready to go with that. Since 4 is the coefficient of x to the first, I take half of that and then square it. And I've got more than that. I've got 13 more than that. Plus 4 plus 13. So there's a summary of what we have so far, and looking to find other solutions for x, I'm using completing the square instead of the quadratic formula. Since I had a coefficient of 1 in front of x squared, then I'm ready to go with taking half of the coefficient of x to the first and then squaring that. Half of 4 was 2. 2 squared was 4. And I've got 13 more than that by having 17. Taking that approach allows me to see that part as a perfect square trinomial. And I again see what happened when I took half of the coefficient of x to the first. That was 2. Factoring x squared plus 4x plus 4 would give me the quantity x plus 2 squared, and then I have the plus 13. So I'm going to subtract 13 from both sides. Take the square root of both sides and include a plus or minus in front of that square root. 13 is not a perfect square, and the only perfect square that will go into that is 1. However, we're looking at negative 13. So by the product rule, I can split up that square root and use the fact that the square root of -1 is I. Some like to write the I in front of the roots. If you write it afterwards, make sure it's clear that it is outside of the roots. And then one more step, and we would have subtracting 2 gives us that x equals -2 plus or minus the square root of 13 times an I outside of the radical. This is where Super Academy left things. And if you're only familiar with just a little bit about complex numbers, then you could stop watching right now and just take the parts where I showed, first of all, by inspection, we can show that a equals 2 as a solution, and that following the approach that Super Academy gave us, although I did synthetic division instead of some lengthy factoring, that we get no more real solutions for x, and therefore we would not for a either. But if you'd like to dig a little deeper, stick around a moment. Okay, so if we take the substitution that the other creator, Super Academy, had suggested we do, then if there are other solutions for a, we could rewrite this exponential equation as a logarithmic equation. The answer to a logarithm is an exponent, so a would equal the logarithm of something in some base. Our base is 2, so by a process of elimination, what we're left with is x. But when we used his substitution of x equals 2 to the a and came up with this equation, giving us that x is equal to 4, or x is equal to negative plus or minus the square root of 13 times an I outside of the square roots. Well, of course, taking the logarithm of 4 and base 2 gave us that a equals 2. But what about plugging these in for x? You might say to yourself, well, how do I do that? How do I take the logarithm of a complex number? Can I even take the logarithm of a complex number? Well, before we get to that, I'm going to rewrite this using the change of base. So we've got a natural logarithm here. Divide by the natural log of the old base. And then what? Well, first off, when graphing, if instead of thinking of this as the x and y axis, if we think of this as the real axis being horizontal and the imaginary axis being vertical, then let's see here, square root of 13. 13 is between 9 and 16. So the square root of 13 will be between 3 and 4. This is not meant to be a terribly wonderful looking graph, just something to give an idea. -2 in the real direction, and then minus square root of 13i, since the vertical axis is the imaginary axis. Somewhere around here, we would have a point representing -2 minus square root of 13 times I, and the other would be up around here for -2 plus square root of 13 times I. You can take that rectangular expression of complex numbers and turn that into what is called a polar representation, where you find the distance or radius of the complex number, the distance from the origin, as well as the angle that it is making. So my radius, or my distance from 0, finding distance the same way you normally would in 2 dimensions. We had -2 in the real direction, square that, plus, now it was either plus or minus square root of 13. We're only talking about how far along the imaginary axis. We don't include the I in this. Square that as well, and take the square root. Squaring a negative, squaring a square root, whether it's positive or negative, and our radius is the square root of 17. So that's 17 that we saw earlier has returned. Now your angle would be found, we call that angle theta. That would be found by the inverse tangent or arctangent. Since tangent of an angle is sine of that angle over the cosine of that angle, then the arctangent, to get that angle, we would be taking the y-coordinate, which is either square root of 13 or negative square root of 13 over the x-coordinate. So how do we then use that? The extension of logarithms from the real number system into the complex number system says this. The natural log of z would equal the natural log of r, where r is the radius or magnitude or its distance from 0 in a drawing like this, plus I times theta. Because tangent is periodic, then we would have plus 2 pi k, where k is an integer. And that's just a fancy way of writing that k is an element or member of the set of integers. So what we have found then is that a equals 2 is a solution. And we also have that the natural log of square root of 17 plus the arctangents of, well, if that were negative, we'd have the 2 negatives canceling out. So square root of 13 over 2, the arctangent of that, plus 2 pi k, where k is an integer, all that multiplied by I, and natural log of square root of 17 plus I times all of the arctangents of negative square root of 13 over 2 plus 2 pi k. All 3 of those are solutions for A. Know a little bit more about polar representations, then you could plug these things in and check that all 3 are working. That's all I've got. Hope the earlier alternate approaches are helpful, and that if you stuck around for the learning about the complex numbers, extending logarithms from the real number system to the complex number system, that you found this informative. Stay safe and healthy, and I hope to see you in another video. Take care.